Hello everyone, welcome to the GeekNarrator podcast. I'm your host Kaivalya Apte. In this episode, I am talking to Patrick McFadin from DataStax, and I'm talking about a super cool technology, a super cool database that is Apache Cassandra. So welcome Patrick to the episode, and let's start with a little bit of introduction.
Well, thank you, KB. This is cool. I mean, we were just talking just before we started, and this is my favorite place is to talk to people like me who are just geek out about technology and love developing code. So yeah, that's probably the most important thing about my background. I'm a total nerd. My background has been in infrastructure. I've been doing this for about 30 years now.
Wow.
And yeah, I'm older than I want to admit, but I started doing infrastructure before the internet was a thing, and then started doing internet things, and it just turned into I started working in the .coms in the early the late 90s, and got wrapped up in all of that. Formerly, my background is in computer engineering and distributed systems. That's what my degree is in. I did undergraduate work there. So it's always been my first love is distributed systems. And the time that I got started, it was writing C++ code on Sun systems. So that was distributed data. But yeah, after the .com crash, I got back I was doing infrastructure at scale, and that's really what got my journey going on working with scale databases. And eventually in 2011, I started working with Apache Cassandra. There's just a few of us. It seemed like, and there's just so many choices, but I got really into it and decided to turn it into a full-time job and joined DataStax in 2012, almost 10 years ago, and have been working on the Apache Cassandra project pretty exclusively since then. And I also work on Apache Spark and Apache Pulsar. You'll see talks that I do on that. Those are also distributed systems, but and I work in developer relations right now, but I still do a lot of work with the Apache Cassandra project and Pulsar project.
Awesome. So excited to have you on this episode, and I'm pretty sure this is going to be like a very super cool kind of a masterclass on Apache Cassandra, right from Patrick McFadin. So I mean,
I hope so.
If you, to our viewers, if you just go on YouTube or just Google Apache Cassandra, like you will see like top 10 lists, and it will name Patrick McFadin, and he is going to have like a good tech talk, some podcasts, some sessions on Cassandra. So do search after you watch this episode and like learn from Patrick. So let's get started on Apache Cassandra, right? Let's start with very basic, like history of Cassandra, how and why it was developed. So if I remember correctly, so Dynamo, this famous paper was released, and Bigtable was also there, and then Cassandra was developed. Why was it developed, and what problem did it solve?
Yeah, you mentioned Dynamo, you mentioned Bigtable. I mean, all of these are papers that were written. Again, it's like when I was trying to scale things in the the early 2000s, like everybody was doing that because you look at technologies like Google, like companies like Google and Facebook. Those are companies that were Amazon. These are companies that were starting to ramp up some serious scale. They were getting a lot of users, and with users comes data, and with data comes all kinds of new problems. And the burgeoning problem of data, right? We just had too much data, and we couldn't just stuff it onto one MySQL box, or worse, trying to put it into Oracle and scaling it until you run out of money. So. All those papers that you mentioned, Dynamo, Bigtable, there was a lot of those and there's other papers involved in that world as well. But, they all were addressing different problems. Like the Dynamo paper was like, how do you keep a database consistent, fully distributed, share nothing? Like what are all the concepts there? Yeah. Bigtable was about how do you build a data model that is performant at petabytes? And, two very different concepts, but So a couple of guys, well, actually one of them, Avinash, who's on the Dynamo paper, went to Facebook, met up with Prakash, and those two were working on a problem at Facebook around inbox search. And again, this is a time where the technology you could take off the shelf was not doing the job. And we were all inventing databases at that point. This is a classic problem of this didn't work. We're reinventing it now. And there were a lot of different choices. I mean, for sure. I mean, you look at like what was happening in that space. I mean, in 2010, around that time, 2009, if you were to just go out and look for like what kind of distributed NoSQL databases are out there, it was just an incredible choice. But some of them were, ridiculous. Some of them were mainstream or like going mainstream. And it's just like anything else, that technology starts to grow up and become like the standard. But at Facebook, and this is what everyone loves to talk about, like Facebook rejected Cassandra. Yeah, I mean, Avinash and I've talked about this. And I think what it was is, because there were so many different choices, then there was a team, the HBase team at Facebook was, and I know a lot of the people that were on that team, they were dominating a lot of that scale database discussion. And they were saying, well, why don't we just standardize on HBase? The thing that was cool is that Avinash was really thinking in the future. And he's like, you know what, why don't we, I believe in this, first of all, this is the right thing. It's a Dynamo and Bigtable. And he donated it to the Apache Software Foundation, which really gave it its life. If it was just another project at Facebook that got stuck in the back, we would have never heard of it. But because it went to the Apache Software Foundation, that's when it really started to take off. And that was around February 17th, 2010. That's when that happened.
Oh, wow.
Yeah.
Nice. So in your words, if you have to, describe what Apache Cassandra is, like in shortest form, what is Apache Cassandra?
Yeah, well, I mean, first and foremost, it's a database. It's a transactional database, meaning that Cassandra needs to be as close to your customers as possible. And it's built for applications, and that's the primary use case. It's not like, for instance, analytics, which is more in the back end or the back office. This is right up close to your users. But it's I think it's regarded as a NoSQL database. It has a wide column data model, which means that to use it, you have to think a little more about how you use your data. It's not just a general purpose database where you say, well, I'll normalize my data and then figure it out in the query. You really think it's a database for applications. And I think one of the most important things about Cassandra is that it gives you the least amount of trade-offs for building applications. It scales linearly. It's very difficult to bring down. It has this really good self-healing and uptime guarantees, and it's distributed. You can do multi-master, like multi-data center, active. So as a database that has all the features you need for modern applications, that's what it's for.
Yeah, awesome. Yeah, I think that makes sense. So if we had to compare and go a little deep into, the comparisons between, let's say DynamoDB or HBase and Cassandra, like what is different? Like they all scale well. They have, all these fault tolerance in place. They also scale linearly. Probably HBase has a different architecture. It has like a master oriented architecture, and Cassandra has no master, right? But what is the primary difference if we have to call it out?
Yeah, well, it's that shared nothing, where every node is independent and coordinates with other nodes. That's such a critical core piece of the architecture. The Dynamo and HBase both have some sort of single point failure to work with. Like HBase has a name node. If you have your name node goes down, you've got no HBase. Dynamo is a coordinated database as well. But I mean, Dynamo is a service, though. No one has ever installed Dynamo, so you would not know that. And that's just a different class of database. You're renting a response to an API call at this point. And it's really funny. I think a lot of people, they just get a little confused. Like, well, there was the Dynamo paper, and then there's DynamoDB.
Yeah.
Is it the same thing? And no, it's not. If you look at, I think that if we've gone through this enough, but just so your listeners know, they are definitely not the same database. They had the same name because Werner, Werner Vogels, who's the CTO at Amazon, really didn't want that name to go to waste. And, they had a good idea, and it did embody some of the qualities of the Dynamo paper, except not the same. So when you get into a shared nothing architecture, it opens up a lot more possibilities, and especially around the amount of self-healing that's involved, and the resilience and the uptime, partition tolerance, those kinds of things. I think in database terms, we talk about, this database avails itself to availability and partition tolerance. And we'll talk about that. We could talk about that later, like what all that means. But just knowing that that's its first principle of architecture is distributed. HBase is kind of halfway there, and Dynamo is definitely not there. I think those are some of the big differences. And there's other, if you use like relational databases, that's a single point. And you can have read replicas and things like that, but that's not a distributed database.
No, yeah, that makes sense. Great. Let's, before we dive deep into, how Cassandra works and how operations in Cassandra work, let's define what do you mean by shared nothing architecture?
And that's a great question, because we could say shared nothing, but a little bit is shared. When we say shared nothing, what is not shared? And in any distributed compute paradigm, you have resources that you're using, and the three resources that we use are compute, network, and storage. And whenever you deploy something in the cloud, that's what you're renting ultimately. And so the compute and the network and the storage, if I'm not sharing those, that gives me some choices. And so just an example, a Cassandra cluster is a logical paradigm. It's like, okay, this is a collection of nodes. And each individual node is independent, but the nodes themselves have to manage their own storage. They manage their own network connections. They manage their own queries. But they also do coordination work, which is really important. And that's what I mentioned, is a shared nothing but coordinated. So when new nodes are added to the system, they're given a seed node or just an IP address of a running node in the cluster, and then they discover the rest of the cluster. Really, the key part of how to make this work is that that coordination is in responsibility. So every node is responsible for a certain range of data. And some replicas of other nodes' data. So you don't have to do the heavy coordination like an ACID transaction. Like if you commit data into the system, it doesn't have to ask every other node in the cluster. So if you have a 1,000 node cluster, it doesn't have to wait for 1,000 responses to say yes, you can go ahead and commit that data. But and we can get into some other things like later about like consistency, what that means. And it opens up the different kinds of consistency, and that eventual consistency is what we talk about in a shared nothing system. It doesn't mean that it's just throw your data in the database and good luck. But you think about like a loosely coordinated system like that has the best chance of uptime. But we put a lot of guardrails around that so that your data is always consistent. Like when you write data into the cluster, that you have every guarantee that it's going to be saved to a disk and it's consistent.
So there's no data loss or anything. So we have those basic guarantees. Cool. With that, let's understand how like typical writes work in a Cassandra. So we will go a little bit deeper into how to model data or database in Cassandra. But let's say I have a table and I want to write some data. So when I do that write operation, what is exactly happening behind the scenes?
So going to like what the Dynamo model originally discussed, like how do we distribute data? It's based on this concept of a partition key. So one of the ways, and I think all your listeners will appreciate the way I characterize this, is thinking of Cassandra as like a distributed hash map. And each hash map has a partition key that points to each individual hash map. And those hash maps all exist on individual nodes. So, okay, so that's a conceptual viewpoint. Without pictures and whiteboards and stuff, we're going to do this with words. So when you write data into a Cassandra cluster, part of that of an insert statement includes a partition key. And that's part of the data model. We could talk about that later. But the partition key is really important because the partition key gets transformed into it goes through a process that it goes through a distributed hash algorithm. It gets transformed into something like a murmur3 hash. And that consistent hashing algorithm, consistent hashes, if you put the same data in, you'll always get the same hash out. So that's the consistency. But when we do that, that hash that comes out is a 64-bit number. And that 64-bit number is a part of a range of all 64-bit numbers assigned in the cluster. So like I was saying, like each node has a responsibility. Well, a node may have just like, if you have 4 nodes, each node has 1/4 of that range, 1/4 of the range of all of 64-bit numbers. So when you insert the data into a cluster, you can write to any node. Any node will accept a write. But when the write gets to the node, the coordinator inside of the node says, okay, I'm looking at the partition key. I am aware of every token range on the cluster because that's part of its own makeup, its coordination. And then it says, okay, who gets this write? And let's say that, oh, it's me. Okay, great. Then that write will then go to the query processor. And it's a very lightweight query processor. And that's when you get into node local operations. So you went from cluster to node. Okay, so this write that you've given it, like you're inserting a user record or something. That partition key now is going to do a lookup, or it's going to put the commit to the commit log first. So it goes writes to disk first. So there's your strongly consistent write, durable write, I should say. And then it writes that memory that insert into a mem table, which is a hash map. And then it acknowledges the write. Now there's other things in there as well. Like if you're asking for certain consistency levels, then it has to coordinate with other nodes. We'll get to that in a bit. But just node local, writing to the mem table and the commit log is the very simple, pure, easy write path for Cassandra. It doesn't do random writes. It doesn't have to read a data file and insert the record into a B tree or something like that. And that's one of the reasons that Cassandra is very efficient with writes, because it's just a commit log is just a log file. So it just appends to the end of this log file consistently. We'll take a break for a second. That's a lot of information.
That is a lot of important information to understand how writes work, right? So it can go to any node. It uses this partition key to figure out who should own this write, right? And then it's written to the disk or the mem table, and it's not updated in a B tree or something, but it's just appended in a log and then probably later compacted and kept in a certain order. And
that's what happens later. Like when you write it to the mem table, and I think this is where there's some confusion, like, oh, it's an in-memory database. No, the commit log is where it's stored on disk and it's in the mem table. So for instance, if a node goes down in the middle of that, when it comes back up, it replays the commit log into the mem table first, so that it pulls that durable data off the disk, puts it into the mem table. But you're right. After a while, you can't run it. It's a Java process. You can't have infinite memory, nor would you want to, especially if you're storing terabytes of data. So there's a process that will flush that mem table down to the disk to make it durable there, and that's called an SS table. And when that happens, then it goes over to the commit log and deletes that segment of data. It says, okay, I've got it on disk. We're good. You can eliminate the commit log. And so that is just shifting the responsibility of durability. So it goes from a commit log, mem table, SS table. Okay, once it's an SS table, the commit log can go away and we can just keep writing data.
Yeah, that makes sense. And then I think this is done so that if the machine goes down, it doesn't have to, read all the messages in a commit log, which can be huge, and replay all the events, because that will take a lot of time to just start up. So it just loads up the the SS table, and then reads whatever is pending. It's not there in the SS table, right?
It doesn't even have to read the entire SS table when you start a node. And a good thing to mention for operators out there is, one of the nice ways to shut down a node is to flush it first. And the flushing, what it does is it spools out, it dumps all the mem tables to disk, spools out all the commit logs, so that when you start it up, you're not having to read a huge commit log. It's just, okay, I'm back up. But that startup sequence, all those SS tables, they're just indexed. So there's just a header, and it's like, okay, I know because each SS table stores certain partition keys in it. And so it just needs to know where those partition keys are.
Yeah. Makes sense. Great. And how many copies am I making? So when I write certain piece of data, how many copies I'm making here?
Yeah, we're starting to get in a little bit of the data model, but not completely. The logical data model of Cassandra, if you have a single node that can store data, how does this become a replicated database? And that goes into like when you start creating the logical model for your data. The first stop is creating a key space, and a key space is a thing that stores tables, 1, and 2 stores replication information. That's it.
Okay.
And so when you create a key space, which is kind of like a database in like MySQL or schema, but the key space part of that, like I said, is the replication information, and it can be as specific as this data center has this many copies of the data, and that one has that many copies of the data, or you can just say, I need 3 copies of my data. By the way, the answer should be 3.
Yeah.
Always. Unless you know why you don't want 3, I'll just save you the trouble. All your listeners can just not have to look that up. 3 is a number that we've learned over the years is a really good replication number for data like this. It's the right amount of protection without blowing out your budget for storage. There are reasons to do more. There are reasons to do less, but 3 is usually a good starting place. So, so if, let's say your key space now is a replication factor. That's what we call a replication factor of 3. That means that every table that gets created inside of that key space will now have 3 replicas. Okay, so what does that mean? Where does it replicate? That's how nodes coordinate with each other. So each node, like I said, we have this 4-node cluster. Each node is primarily responsible for 1/4 of the data. And when we replicate data, I'm trying to make sure I explain this in a way that doesn't sound convoluted, because I've explained it so many times. You get into this place, and you've probably been there too, where you're like, oh, it's obvious, but it's only obvious in your own mind. So when we talk about replication in that 4-node cluster, and we say replication factor of 3, that means each node now has its own primary range. And also 2 other nodes worth of data. So each node is actually storing 3 copies of data, 1 from itself, and then 2 from other nodes. And this is a good concept too. Like if I have a 4-node cluster and a replication factor of 3, okay, that means each node is storing 3/4 of the data. But if I had a 1,000-node cluster, each node is still only storing 3 nodes worth of data. And that's really critical. It's not trying to replicate the entire cluster. But when you have a node that's storing replicas of data from other parts of the cluster, now this opens up some opportunities. Now, if I have 3 copies, if 1 node goes down, or even 2 nodes go down, I still have my data. My complete data picture in the cluster is available. And that goes all the way back to the Dynamo paper of how to maintain a database that is available despite the horrible things you can do to your, the hardware.
Yeah.
Shutting down nodes should not bring down your system.
Makes sense.
So I'm going to pause there. If you have any questions there, and then we'll move on to how do you keep it consistent?
Yeah. So I think that's going to be my next question, right? So when is the actual write happening? So is the client waiting for these 3 writes or 3 replica writes to happen, or it is not waiting? So how does that work? Is it like asynchronous replication or synchronous replication?
Well, this is where you, the developer, KV, can make some choices. And Cassandra gives you the ability to make choices based on your use case. And that dial that you can turn is called consistency level. So the replication factor of 3. So replication factor, it means this is how many copies I have. But the consistency level is how do you want to treat that replication? And it's pretty powerful. So you can dial it, this is why I say eventual consistency. All right, let's dig into that a little bit, because it doesn't mean that it just, like you were saying, like, is it just asynchronous when you set data into the cluster? Like eventually it will show up over here. Yeah. But no. The consistency levels go all the way from the strongest consistency, which is all. So meaning that when you write data to one single coordinator, it will then talk to the other replicas and say, okay, here's some data to insert. It will have to commit the data to disk and reply back to the coordinator. So those 3 nodes all have to agree, yes, it's on disk. And then it'll go back to the developer or to the user saying, okay, the thing that you wanted to set at consistency level all is now on every single replica. Yeah. That is probably you'll never use. And the reason being is because when you have consistency level dialed to all, you have no chance for a node to go down. Yeah. If a node goes down, you can't satisfy that consistency level at that point. That's basically where ACID transactions or ACID databases fall. Is if there's a failure of any kind, it shuts down everything for good reasons, right? It's like, nope, I can't guarantee anything. I'm not going to give this to you. The consistency level, which is most typically used and the one that you should really get used to using, is the one we call quorum. And quorum is 51% of the replicas acknowledge the write or the read. So let's say here's a scenario that you want is when you write your data at quorum, it will asynchronously send out those writes to all the nodes. It doesn't just pick nodes. It sends it to all of them anyway. It only needs a reply from 2 nodes for 51%. So 2 out of the 3. It only needs a reply from 2 of them to acknowledge the write. Now, the third one, what's going on there, it could be that you took it down for maintenance. It could be that it was just slower and it didn't respond as fast, like it was somebody was G-zipping an entire directory or something. So it's avoiding problems. This is an instance where Cassandra is helping you avoid problems. But the consistency level is maintained, and whenever. So let's say that you did bring that node down. Well, when the coordinator, because it couldn't write to that node because it was offline, it will store the write locally. And it'll say, it's like when you maybe go on a trip and your neighbor hangs on to your packages, something like that. It's like that. But when you come home, you're like, hey, do you have anything from Amazon from me? Because usually you do. And that's the way the system works, is when that node comes back online, other nodes that have stored data for it have been like, hey, welcome back. Here's all your data. And then that data becomes consistent on that node, and it's good to go. So this is that self-healing part of it. The lowest consistency level is 1. Well, there's a lower one, but I'm not even going to talk about it because it's horrible. Don't use it. 1 is just one node needs to reply. And that's, for like a great use case for that is like IoT.
Yeah.
It's like I'm just pouring data into my cluster. I don't need it consistent right now. This isn't like my user accounts or anything like that. This is just I'm willing to deal with the trade-off. But the big trade-off, the reason you go from all quorum 1 is the speed that you get a response.
Yeah.
And when at quorum, it may be a little slower than just one. One will just write the data.
Yeah.
So it's kind of an overview of how consistency level, but I think the takeaway here is when you talk about replication factor, as a developer, you instantly think of consistency level. How do I maintain that?
Yeah, that makes a lot of sense. And I think tying this discussion back to what you said, like 3 is a good number, right? Is it good because we get like a majority of 51% for quorum level consistency? If we add only 2, or 1 is a different story, but if we add 2, we cannot make a majority, right? So is that the reason that 3 is the right number to start with?
Yeah, it gives us, I think there's been plenty of studies that have shown that, for a failure domain, having 3 nodes fail completely is, for a lot harder statistically, especially if it's laid out properly. There's that. But it's also that odd number gives us a better, less waste when it comes to things like quorum. So 51% is 2 out of 3. If you add 4, then it's 3 out of 4. So again, here you go again. So it's not 2 anymore, it's 3.
Yeah.
So, and then if you add 2, then you might as well just use all or 1 at that point. You should never use quorum. Yeah.
Makes sense. Great. I think I have some more questions here, but let's go a little, on a different side. So I have written, data. I have my replicas. I have set the consistency level. It's all good. Now I want to read that data, right? How does it work, and how does it affect the consistency based on whatever I have set in the configuration?
Yeah, the way that Cassandra reads data, I think, is one of the more magical parts of distributed computing, because this is when all that good stuff that you set up pays off, right?
Yeah.
Because I think this is when I tell people about how it works, it starts to click. It's like, oh yes, this is a very elegant system. All right, so with all that set up, let me tell you how it works. So when we wrote the data, we used a partition key, and that partition key was consistently hashed. Murmur 3 is our choice right now. And so that consistent hash means that anytime I pass that partition key through, I get the same 64-bit number. Okay, so that's when I was setting my data. Same thing applies to whenever I'm reading my data. And the name of the game for the client, like your software, whatever application you're writing, I want to get to my data as fast as possible. I don't want to have to scan through the entire cluster. That's a Spark job. And so by passing it, and this goes to the data model, in the where clause, you pass it the partition key. What you're doing is you're giving, if you have 1,000 node cluster, huge cluster, and these are very common. Biggest clusters I've seen are like 4,000 or 5,000 node clusters. But if I give it a partition key, it's only going to one node.
Yeah.
And it's 2 replicas, right? Or it's 2 replicas. And that gives us a chance to get our data quickly. In a petabyte of data, I just want that one thing. And so that's the first stop on the read, is that it uses the partition key to go to the node. When it gets to the node, excuse me, it uses the partition key, then gets used to find the SS table that's on the disk. And that's there's a mechanism that it goes through that has a bunch of really cool things like Bloom filters and key caches. But it's going to read that, find the SS table quickly on disk. And then this is our friend Bigtable. This is what Bigtable brought us, was now the data for that partition key is laid out in a linear fashion on disk. And so that we can, when we say, I would like to have this partition key with this data that's involved, then it just, on the disk, it goes down to the partition key and just reads that data linearly from the disk. So it's a very fast read for large volumes of data on a partition key. That data is put back to the coordinator. A really important thing here, now back to consistency level, is if you say, I want to read a quorum, it has to match the coordinators. The coordinator has to match up with the read that was done on another node.
Yeah.
And they have to match up mainly by timestamp. If this timestamp is the same as this one, and you have two of those that are the same, the read is satisfied at quorum, goes back to the client. If they don't, if they're not satisfied, like let's say that one says this is older, and then the two say that you're the newer data, it'll take the newer data, but then those nodes will then go correct that other node and say, you got it wrong. Try again. So there's these little mechanisms in the read, we call it a read repair, that keep things consistent. But the reads can be really fast. And I think this is something that a lot of people thought. Well, there was this myth around Cassandra is great for writes, but terrible for reads. Not true. It's very fast. You should get like single, double digit millisecond reads consistently with the right data model. Yeah.
That makes sense. Great. So I now know, how this reads are working, and how does it find the node, because it has the partition key, and there is some mechanism to reduce, like for example, Bloom filters to reduce the disk seeks. And then the way it is stored in disk, it can just directly scan through it and figure out where's the data. That makes sense. And what happens to the read consistency? So if I said I think you mentioned that it uses the time to figure out what value does it have? Is it stale? Is it latest? Who generates this time, right? Where is this generated? Is it on the table, or I have to pass in the data, or is it generated on the Cassandra node? Yeah,
and it's typical for any distributed system to be really dependent on time. You think of like, was it the Spanner paper from Google? They used an atomic clock, the Armageddon master, to do these really high precision timestamps. So where does that time get handled? The client can provide the timestamp. That is not the ideal place. I mean, and this is a typical answer for anything Cassandra is. We give you a lot of choices. It's meant to be a very flexible system, and that's why you get these. There's a lot of different answers, but you can do it on the client. When you write your data, you can provide a timestamp. That is one way to do it. Otherwise, it's done on server side. And one of the reasons when you're administering a Cassandra cluster, you really want to make sure that your time sync is really good with your clusters. Drift is, of course, a huge problem with any server that you deploy. And one that I think has been handled really well in later versions of the Linux kernel and newer projects with higher precision time. But it's you should just use the server side version of that, and that's included is part of the metadata for the column that is stored into the database. Yeah.
Okay, makes sense. And I've seen, so I have very limited experience with Cassandra, but I've written some queries, something like SQL, and it provides me an option to provide this allow filtering clause, which is, I think, not recommended to run on like a production database because of performance reasons. So can you throw some light on that? Like, what does allow filtering do, and why is it not recommended?
Yeah, it's a really timely discussion. We're actually in the middle of, and by the way, when I say we are in the middle of a discussion, this happens on the Apache Cassandra mailing list or in the Apache Cassandra Slack. This is all done in the open. So there has been discussions about like, what do we do about allow filtering? You mentioned like we have our own query language, Cassandra query language, or CQL. It does look a lot like SQL. I was one of the people that was in the initial spec for that, and that was a purposeful thing. The original data model for Cassandra was Thrift, so it was a key value pair, the RPC framework, and that was not programmer friendly. It was very difficult to work with, and so CQL was where we decided we need a much more standardized query language. It looks like you can do selects, inserts, updates, that sort of thing. And that's exactly what you get.
Yeah.
The thing that trips people up, I think, is when you go from SQL, which is, SQL 99 or whatever you're using, where you get a lot of syntax. And the where clause includes things like joins or, you can do subselects and things like that, which are not a part of Cassandra. Cassandra doesn't do joins. So what happens is this is we always, and you'll hear me in some talks talk about this. It's like, this is the unfortunate thing we created with CQL is that when people, the first time that they log into their database and there's a table of data, they do select star from database, from table.
Yeah.
And they get 1,000 results back because that's the limit of a single query.
Yeah.
And they're like, oh, well, I want to see everything. I want to do select count star from table, and you get 1,000. Like, wait a minute, I know there's more than 1,000 here. And then in the CQL syntax, it'll say, well, that was a limited result. To get more, use allow filtering.
Yeah, so I've seen that.
Yeah, select count star. This is the debate we have. It's like they basically told people like, oh no, you didn't feed out enough rope to hang yourself. Here's a whole lot of rope. Because what's happening, and this is I think this is the fun internals part of it, is because when you say select star from table and you're not providing a partition key, let's go back to that read thing that I was talking about. The partition key sends you to a specific node and a specific SS table, and then you read linearly across the disk. What happens when you don't provide a partition key? Well, then it's up to the coordinator to just look at the token range for the entire cluster and say, let's go for a walk. And it just goes through every single one that it can.
Yeah.
And we've purposely limited it to 1,000. And because you don't want to, do a query and then see your cluster dim the lights. Like, what happened? Yeah. But that's what allow filtering will do. And there are use cases for sure where allow filtering does make sense. But especially with, this is where we're debating. It's like we should enable the right use cases and dissuade the wrong ones. But that's what allow filtering is doing is this, if you've done a full table scan and you tried to avoid a full table scan in like a SQL database, this is a full cluster scan. And it's that much worse.
Okay. Now I understand what happened to my production database.
Well, KV, this is a good plug for the latest Cassandra that's coming out 4.1 is it has this thing called guardrails, and it blocks, it lets the operators put in anti-pattern blocks. So if you show up and you're like select star for database, allow filtering, you can turn off that activity so you don't have some random person bringing down. It won't bring down your cluster, but it sure will cause havoc.
It will. I mean, there are so many answers on Stack Overflow that, hey, just add allow filtering and you will get the data. And no, but it's not recommended. And now we know why, because it doesn't have the partition key. So it has to scan like everything because it's asking for everything, right? Great. So with the next section, I want to move to a little bit to understanding the data model from the application's perspective. So I heard or I watched a couple of tech talks that you have given around data modeling, and you said that in the old world of relational database or database modeling, we started off with the data, we started off with the entities that we want to define, and then we moved upwards to the application, and then we decide or design the queries that we want to support. But in Cassandra, we do the reverse, right? We start with the application, and then we slowly move towards data. What is different, and why is that recommended?
Yeah, we've done some great work here to prepare everyone for the answers, right? And it is just in the way you're doing things that are much more sympathetic to how the database is designed and for what you want than the other way around. I mean, in full disclosure, I've built SQL databases. I've maintained SQL databases. I have all my Oracle tickets. You know, I'm an Oracle DBA. So I love SQL databases for what they can do. They're very powerful. I love the expressivity of SQL. You can I still write SQL queries. I use the big table for a lot of our data warehousing stuff still. So this is not a thing where it's like, oh, SQL is horrible, you should never use it. The thing that I think everyone should realize is that when, you know, this is my experience, my journey through writing application code and deploying things in production with an SQL database, eventually you get to the point where you have to denormalize the tables because the joins are becoming a liability. And it used when I ran infrastructure years and years ago, we would always like monitor our like different pages, and we'd have alerts if our database queries went over 250 milliseconds, we would start getting alerts. And invariably it would be like some ridiculous join that somebody was doing. And you know, it's like, okay. And our DBA team would set about denormalizing the queries so that we would put everything into one table. And that starting thing, that what that is, like where you denormalize your data is where you should start when you think about writing application-based data models. And so it's not anything we haven't done. It's just that we haven't started there. And I think this is where people really get tripped up with starting with Cassandra, is that they're like, it's not flexible enough for me. I'm it's going to work against me. It doesn't give me the agility. So I think it can. And let me explain the method that I've always used that I've been successful with. Is first and foremost, start with your application. If you look at, you know, everyone does the whiteboard, the block diagram, you know, all the different things that you do when you're starting your application. Like, this is what my application is supposed to do. And when you look at the data, like, you can start looking at your application as a series of data domain, already like it's a data model. And like when you log into the account, we need to have a user table with the password or like linked to a hash or something like that. Okay, so we need to be able to look up by their username. Okay, there's that. And then here's their profile information, we just need an ID for them. I mean, you start looking at all the things where you need data. And pretty soon you can start seeing like how you would query that data. Like when I log in, I'm going to need to pass it a username and a password. And I'm going to have to look up the username in the database to find the person. Okay, are you a user? Whenever I'm logged in, I now have an ID that's a part of my session. I'll use that ID to look up like all the comments that I made on something like part of our application, or I can use it to look up my profile. So you just think about those the application workflow, the application flow, and you start thinking about where I need data. And that's not crazy. It's just a different direction. And I would argue that even if you started with a domain of data, like here's my user table and I'll join it with like my comments table. Okay, now I'm going to go write my application. Your data model is going to change 30 times. Because it's like, oh, I need a new row. I need a new column. I need to index something. Oh, I need a different kind of join. Maybe I don't want to do a join anymore. I want to denormalize it. So things, you know, as you're building an application, things evolve. But with Cassandra, once you have those queries, you're like, I need a user table. I need a comment table that has a user ID on it as a primary key. Now you can go build those tables for exactly what your application needs. And a data model in Cassandra, it's create table, very familiar syntax. You create table with the column names in it. You create a primary key, and that's pretty important. That's the most important part of your data model is the primary key, just like every other. But you get a table of data. Now you have rows and columns. And in your application code, you start thinking in terms of, here's the key to get the data that I need at this moment, at this page, at this transaction, or whatever. So I think from a high level point of view, from a programmer's point of view, that's how the data model works for Cassandra.
Yeah. Yeah, that makes a lot of sense. And I've been in the same position where I've said, oh, this is not flexible at all because I think we modeled it the wrong way. And we tried to fit in that relational data model into the Cassandra's model. And that's when it gets into, it gets tricky. And I think for the older, like traditional relational database systems, they were trying to optimize around disk space, right? Because disk was, expensive, but now it's not. And now I think most of the applications have those workflows and, people say, start with the customer, like what they want, and then design your application and not the reverse. So I think it makes a lot of sense in today's world. Let's take an example here, right? So I think you mentioned on some of the examples, but let's take a very small example and then we'll understand what kind of, how can I make my queries faster? What kind of indexing options we have in Cassandra. Let's say I'm developing a chat application where I'm just showing, or, I'm chatting to my friend and I use Cassandra to store, whenever I send a message, I store who sent the message to who, and then the actual message, and let's say a timestamp. And I want to get, the history of messages that one person has sent to the other. Do you think Cassandra suits well for this type of application? And if yes, what should be the primary key?
Ooh, great question. Okay, let's do some live data modeling here. So it's funny because this is just where you get as a Cassandra developer and someone who's thinking about I was already like picking apart your data domain and your data model as you were talking about like what these things are. So I think what you're talking about, and let's do this together.
Yeah,
I think what you're talking about here is a time series model. Am I right?
Yeah. Something like that. Yes. So it has a time component to it.
Yeah, because I think some people argue every data model is a time series model eventually.
Yeah. That makes sense.
But I mean, you mentioned a couple of things here which are important. Is I have two people, and they're creating data asynchronously and bilaterally. So this person sends a message to this person, this sends a message to this person, and so they need to know like. And so the queries we're talking about here, like when you mentioned is, as a user, I want to see all the messages that I sent to a particular user, right?
Yeah.
Or just all my messages, period, or both?
Yeah. I mean, let's say a chat history. Like if I open up the chat application, I see a history of messages, and I keep scrolling and I get the older messages, and I keep scrolling and I get even more older messages. So I want to see the chat history like both ways, right? So there's both of us has a user ID, for example, and the direction of the message may be important in this data modeling, and then the message itself. And of course, it has a time that when I send this message or when I receive this message.
Yeah, I think of the simplest data model, of course, would just be a table that stores from a certain point of view. Like, so I want to see from my point of view, like you and I are messaging each other. The primary key that I would use is two-part, is my user ID and your user ID would be the primary key. So it'd be primary user ID and friend user ID. So those would be the two partition or the two keys that I would use. The way we do primary key in Cassandra is there's two parts. There's the first component is actually what turns into that partition key that I mentioned earlier. Every column that you add after that is actually called the clustering column. So if I say, here's a primary user ID as a partition key, and then friend ID is the clustering column, what that's doing underneath is I'm setting up a thing where I can say, and then in that data model, we would have just maybe the direction of the message and then the text of the message. So like the directionality. So we have, for instance, we had a nice long chat. I can go in there and I say, I could say select user ID, friend ID from this table, and it will give me an ordered version of the entire chat.
Yeah.
And then if I wanted to get a little more creative with the clustering column, then I can maybe add the direction. Like I don't want to see only outgoing messages to my friend or incoming messages to my friend.
Okay.
So these are what I'm doing is I'm adding to that clustering column on that part in that primary key.
Yeah.
Here's what's going on down on the disk. And this is really the key. And this is what really pops. It makes people understand why we're doing this.
Yeah.
First, the partition key is that my user, or the primary user ID sends you to a particular node. Yay.
Yeah.
What the clustering column does is it then gives you a sorted order on disk for after that partition key. So remember the linear reads. So whenever I read data, I take the partition key, go down to that file, that SS table. Then I look up the friend user ID, and then they'll all be in an order. And if I include a timestamp in the primary key, now they're in time order. And that's kind of what we want to do, is start thinking about like, now I've built out this query where I'm saying, I want to see the entire chat with my friend in time order. Now I could say the primary key is partition key is going to be my user ID, my friend user ID, and then the timestamp. So when I look at the disk, I'm going to see a partition key of my user ID. Then I'm going to, everything past that is going to be the friend user ID with a timestamp in timestamp order, and it'll be linearly arranged on the disk. So whenever I do a read, it just goes slurp, brings it all in one shot.
Nice. Yeah, that makes a lot of sense. And just to clarify, so we have like these three parts to the primary key. One is the user ID, and then the friend's ID, and the timestamp, just to keep it sorted. What part of it will be hashed to find the node that I'm want to write my data to? So is it the entire primary key or just the first part of the primary key?
Just the partition key. Yeah. And every column name after that is just it does two things actually, which is really cool. When you create a table, first of all, you're describing how the data should look in the cluster and then how it should look on the disk. But the clustering columns, I should back up here real quick and say, and this is a very important part of a Cassandra table, is all of those columns have strong typing, right? They're a string, they're a timestamp, they're a Boolean. And that, I think that's a great thing to myth bust right now, is that this Cassandra is not a schemaless database. It has full schema. And that is important for lots of reasons. First of all, schemaless can get a little random. You don't know what you're going to get sometimes. And by creating tables of data with real strong type, you know what you're getting. And that makes it easier for programmers for sure, because you can marshal the types. And whenever you create an object in Java, you know exactly what types you're getting. It's not duck typing. We're not using Ruby as much. I mean, maybe you are. But those types actually make have a lot of bearing on what's going on in the data model. And so when you create, I mentioned, these are the user ID and the friend user ID. Well, those would typically be UUIDs. So, because those are very unique numbers, as in the name, but we store those as UUIDs. So that's the type. But if I use a timestamp as one of the clustering columns, the sorting, that sorted string table, the SS table, the sorting and the collating order is based on the type. So as you're writing data, is this flushing data to the disk? Well, let's go back. Remember our write path. When it writes the hash map in memory, it sorts it right then and there. So it's like, this is the timestamp, and this is the temporal order of this, and so this is how it sorts it. And when it dumps it to the disk, it's now in time order. If you use a number, then it's numerical order. If you use alpha or UTF-16 or UTF-8, it's in the collating order there. So ordering that you provided in your data model is how it's actually stored on disk. So you're actually getting sorted data written to disk. And when you read, that's a huge efficiency gain.
Yeah, that makes a lot of sense. I think that part is clear. So this is like a very good data model where I can get the messages in time sorted order. I can probably do some time slicing as well. How about, so let's say, I'm just trying to extend this a little bit so we can talk about the next thing, which I'm really interested in. So let's say I want to keep track of the number of messages a particular user has sent ever. So just for analytics purpose, right? So this user has sent like 100 messages. I don't care to who, but he has sent that message, right? And the user 2 has sent like, let's say 1,000 messages. So I want to increment that count whenever there is a message sent by a particular user. But this is just for the analytics purpose. Now, so when I send a message, I'm writing to this table, which is the primary key, user ID, and the timestamp. And then I'm also writing to the other table, which is increment the count. Is there a way I can, create some sort of transaction between these two that if the other write fails, I also kind of roll back the first write? Or is there a transaction support on Cassandra?
The transactions that you're talking about with a commit rollback are not available. So that's a very difficult problem. And it's actually one that we purposely have made. That doesn't mean that we are not going to do this. We're not talking about the future just yet, but if you look at what's happening in Cassandra 5, there's a lot of that discussion happening now. But right now, if you go download Cassandra, it's 4.0. That is not in a part of it. Yeah. But I think to your point, if you're setting data into two tables, how do you guarantee that those two things happen? And Cassandra does have this concept of what's called a batch. And I will warn everyone, do not think of a batch as the same batch as like an Oracle batch where you send it 10,000 records and it's more efficient. That's not how Cassandra sees a batch. A batch in Cassandra is, hey, these two insert statements are very much, they're aligned. They need to be set at the same time. And so what it does is it sets up a guarantee that it will happen. So it logs the batch. So these are the changes that need to happen. It'll immediately put it into a commit log. So if something happens, that it can replay the commit log to make sure that it happened. But the downside, of course, is if you make a mistake, it doesn't roll it back. But it guarantees that both things will happen, or three things, or five things, or how many things you add.
Okay. So it will eventually happen. So it's not going to roll back or something, but it will happen whenever things come back online.
And it's interesting you mentioned that, because I think this is where people go, oh, then Cassandra's not for finance, which is a mistake. Every bank in the world uses Cassandra somewhere. And it goes into thinking about how you do data models. I would guarantee you that a lot of bank transactions, most bank transactions, are not an ACID transaction. Only because that there's not enough guarantees on an ACID transaction, and there's not a record that it happened. The type of data models, I've worked with banks, financial companies before, on the type of data model that works is what we call a ledger. And it's what it is you create a time series model that marks every single change. So if you're moving money from one bank account to another, you can say, all right, subtract this amount from this account, add this amount to this other account, and put them in a timestamp order. Now, you may do that in runtime in the application, and it may be fine. But let's say something happens. Well, this is what every bank has to do anyway, is reconcile all of this. Mainframe jobs are built around this reconciliation process. So, there are, and like when you get into this really high stakes, very touchy kind of transactional stuff, these linear models, these ledger models, are actually much more, they're much more used in the real world. for that kind of thing.
Okay. Yeah, that makes sense. Great. So let's talk very briefly about, how the CAP theorem works or fits into Cassandra. Like what team the Cassandra chooses, the consistency team or the availability team?
Yeah. So the CAP theorem is, it's an old one, but a good one. And it was Dr. Eric Brewer, who's a fellow at Google now, who has talked about Cassandra a few times. He came up with this thing around the 3 letters of CAP. And those 3 letters are consistency, availability, and partition. And these are the 3 letters, like you get 2. Your 3 letters, you get 2. And it's like the iron triangle of in engineering. But some databases are optimized for consistency and partition tolerance, CP databases. And the consistency is king. That's the one that you're going to have. Those are like your relational databases. Cassandra is considered an AP database where it optimizes for availability and partition tolerance. Now, given the eventual consistency, you can dial it up to a CP database if you want. But normal operations, it should be AP. And AP databases are the kind of databases you need for resilient data. Like, you can have a data center go down and it won't bring you down. That kind of thing. So, that's how it applies.
Yeah. So that's a AP database, but one can configure to make it a CP database. And I think we already talked about these, controls that Cassandra gives. So it makes it so powerful, but at the same time dangerous if you don't understand what you're doing, right? I think that makes sense. Let's talk about the recent features that Cassandra as a community is working. And I think recently 4.0 was released. So what are the new features the community has contributed?
Yeah, so 4.0 is the current shipping version. We're getting ready to do 4.1. It's an alpha right now. Hopefully beta soon. By the time people listen to this, it'll probably be in beta. That's the latest release, really. We spent a lot of time getting 4.0 into a different kind of place as a database, optimized really heavily on having a very resilient database. It should be able to put up with the most abuse and never lose data. This is kind of a first principle for this. The stability is the most important thing. And so things that were added in there were things like, especially for operators, like running large clusters. Because I mentioned, there's a good portion of the world runs on Cassandra at this point. If you pick up a phone, you're probably using Cassandra all day long. Like an iPhone. If you pick up an iPhone, Apple's a huge Cassandra user. But it's just so important to our daily lives. You think of everywhere that you can use Cassandra. What does that mean for people building Cassandra? Well, the operations have changed quite a bit. There's better ways to keep your data consistent with repairs. The transactions that are currently involved with lightweight transactions using Paxos have improved quite a bit. That's a new feature. In 4.1, we were introducing that thing I mentioned to you, the guardrails, which are great for operators who are deploying Cassandra clusters that want to create limits for their developers. You can't add 1,000 indexes on a table and watch it burn. I think these have been in SQL databases for a long time. Actually, this is the argument we had internally. It's like, there are role-based limits. You should be able to do that. There's a lot of maturing features that are going into it as well, such as we're allowing for more choices in the storage model. Right now, we just have one. And we're creating pluggability in that so we can have a variety of storage models. Instagram was pretty famous about using RocksDB as a storage engine for Cassandra. We call it Roxandra. That gave us a lot of... the names are great. It gave us a lot of ideas about what other kind of data models or DataStax we're exploring using object storage as a way to store data. Our Astra Cassandra as a service uses object storage now for a lot of the SS table storage, and so we're looking at all the different ways we can store data that are probably more flexibility, better suited for cloud, that sort of thing.
Very interesting.
Yeah, I mean, just trying to think of all the interesting features that would be for everyone here. Yeah, and the big one is what we're talking about with 5.0 which is full ACID transactions in a way that no other database has ever done before.
Wow, that would be amazing. Great.
Yeah, it's a brand new consensus algorithm called Accord. Maybe I'll come back on and just talk about that sometime.
Yeah, that would be awesome. Is there a white paper or something? I'll be interested in reading it.
Yeah, if you Google Cassandra Accord, ACCORD, there is a academic paper. There's some University of Michigan did some work on it. There's some Apple engineers on there. This is a consensus protocol coming from Apple. Some of the very smart engineers in distributed computing are thinking about the next generation. Like what's after Raft? What's after Spanner? What's after Caesar? This is the next generation of transactions.
Yeah, very interesting. Cool. I want to ask you two more questions, which is, based on your experience. So what is the coolest use case that you have seen where Cassandra is used?
The coolest? Oh, man.
Yeah.
There were some projects that I worked on. I mean, first of all, one of the coolest projects I worked on was on player matching for Call of Duty.
Wow.
I was working on a project with Demonware, which Demonware is a company owned by Activision, which does Call of Duty, the video game.
Yeah.
And I was working on a project with them. And yeah, it does all the player matching and all that stuff right out of the Cassandra database, and it still does today, I think. So that was a cool use case. I was like, I gotta participate in the launch of a Call of Duty game. I gotta fly up to Vancouver and at their studios and participate in that. So I was like, this is way cooler than I've ever done for anything with data.
Yeah. Very cool. Very cool.
Yeah. I mean, interesting stuff. I mean, I think of like some of the things that we've helped. I mean, some of the use cases that I've heard that are just really interesting, like Walmart, big retailer in the US. They use a Cassandra cluster to store every item in every store, so that when you walk into a physical store, you could say, I would like to know where the 5 volt or the 9 volt batteries are. And it will tell you exactly which row and like physical row inside the store and section that those batteries are. So you can just walk right to it.
Oh, wow. Yeah.
And they keep up with, like, as someone buys the 9 volt battery, their point of sale system keeps up with that. And they did a talk about that a few years ago, and it was really cool.
Nice.
It's just, that's what you get with real-time data, right?
Yeah. That's amazing. Great. And, so I think this was a very insightful discussion that we had, and you cleared up a lot of confusion that I had personally in my experience with Cassandra. And I'm pretty sure that, our viewers are going to enjoy our discussion, and you explain all those complicated topics in such a simpler manner. We also did a live data modeling, on a podcast. So that's really cool. And
we did that.
Yeah, we did that. So I'm definitely going to try that on a sample chat application and see how that works. But just out of curiosity, but I think I am more curious to learn about Cassandra, and our viewers will become more curious as well after watching this podcast. And I'm going to add I think you did a data modeling kind of a class with Jeff Carpenter, and I watched that tech talk or a talk. That was really cool. So I'm going to add that in the description so our viewers can actually take a look and, understand how data modeling works with Cassandra and all the configurations that they have to make all the choices that you have, they are really great and really flexible that suits your use case. So with that, I think I would like to thank you for, coming to the episode and sharing all those insights and experiences with our viewers. And I'm really looking forward to, collaborate with you more. And as we discuss, maybe on a white paper on next steps on Cassandra or Accord or, whatever sounds very cool. So we should be doing that again.
Yeah, I can give you some updates. I'm sure there's plenty of other things. We talked for an hour and a half maybe, but there's a lot more to talk about, right?
Yeah.
And if you're interested in using Cassandra, you can reach out anytime. KB found me on LinkedIn. I'm out there. Pretty easy. Just say hi.
Yeah.
And if you want to just give it a shot, DataStax, we work on a Cassandra as a service called Astra. You can just go to astra.datastax.com and play around with Cassandra. And if you're like, oh, that's cool, but I want to run my own, that's cool too. We love people using Cassandra. So if you want to rent it, install it yourself. The Apache Cassandra Slack channel is a place to get a lot of help if you need that. But we're just out there ready to help you figure out your data model and be successful. And
Awesome. Great. Thank you so much, Patrick.
You're welcome. Thanks, KB.